Hello everyone, welcome to our 8th tutorial. Today we will discuss blockchains. Let's start with our first question. So the question says, why is the difficulty of the proof of work in Bitcoin is set to 10 minutes? And what would go wrong if it was changed to 12 seconds? So what is the proof of work that is set to 10 minutes? So the proof of work here means that part where we collect some transactions and create a block. So the Bitcoin blockchain creates a new block every 10 minutes. And this 10 minutes value is an arbitrary value. So this means that there is no actual proof, or there's no mathematical derivation that was used to come up with this number. So basically, every 10 minutes, the blockchain collects all the transactions that was done in these 10 minutes, and it creates a block. So the question here says, what would go wrong if we changed it to 12 seconds? So let's say we here collected these 5 transactions in 10 minutes. So if we are to create a new block every 12 seconds, what do you think it would be like? So I think it would be like something like this, maybe in the best case. It would contain 1 or 2 transactions. So if we are to compare a blockchain with that creates a block every 10 minutes and another one that creates a block every 12 seconds, that would be the difference. Here we would have huge blocks or bigger blocks, and here we would have blocks maybe with 1 or 2 transactions like this. So what's the difference here between this idea and the other? Technically, if we are to talk about the pros and cons for a blockchain, for the blockchain itself, there is nothing wrong about it. So there is nothing wrong in changing it to 12 seconds. But the bad thing is that we will have a lot of blocks with a very little amount of transactions, and that would void the idea of blocks technically. Okay, so let's go to part B in question 1. Early on, Coinbase, a large Bitcoin exchange company, was facing the following type of fraud. A Coinbase user purchases Bitcoins with funds from a compromised bank account and then transfers the Bitcoin to an address that he or she controls. So Bitcoin Exchange, which is a company, was facing fraud where a Coinbase user, an Eve user, goes and gets or compromises a bank account and then uses this account to buy some Bitcoins. Okay, and then after that, this user transfers the Bitcoin to a Bitcoin address that he or she controls, not the Bitcoin exchange Coinbase. When the owner of the victim bank account complains, Coinbase has no way of getting the Bitcoin back from the misbehaving user, since the Coinbase at this point does not know where is this amount of Bitcoin is now. So that's because the Coinbase user, the fraud user, sent them to an account of him that Coinbase does not know about. So Coinbase loses money because it has to repay the owner of the compromised bank account. How can Coinbase solve this problem? Okay, so the problem here is that this fraud Coinbase user took money from a compromised bank account of another person, and uh, this user transferred the bitcoins to an address out of the Coinbase uh, Bitcoin exchange. And according to the question here, Coinbase does not keep track of such transaction. So what would be a solution for this? A good solution for this would be that Coinbase keeps track of such transactions, so that when something like this happens, the company does not have to repay the money to the compromised bank account owner, but in fact they can just forward the transaction details to the authorities, and they can take care of the fraudulent Coinbase user. So in what way should we keep track of such transactions? Basically, we can just use blockchains. So just a quick reminder, in the blockchain, just as we said in the first question, each block contains several transactions. So basically, when the Coinbase user here buys the coins, or purchases the coins, so there will be a transaction here, let's say T1 here in this block, in the second block, and this transaction will be a transaction where Coinbase sends money to the user. This will be the first transaction. And when the user sends the coins to his account, it will be another transaction here, which is T2, for example, where the user sends money to his own account. And this will be transaction 2. So this way ensures Coinbase to keep track of whatever is happening, and they can keep track of every coin they issue or they sell, so that whenever something wrong happens, they can go and check what happened and trace the transaction. Now with part C and the first question. The question says, suppose that you want to generate each student's draw number for a housing lottery as a hash of student ID concatenated with the block ID, where BI is the ith block header in the Bitcoin blockchain. To make the scheme more secure, your friend suggests using a hash of student ID concatenated with the header of the block BI-1 and concatenated with the current block header. Instead, what does this buy you in terms of protecting the scheme against manipulation by miners? So let's explain the difference here. So h of student ID concatenated with BI will be something like this. So if there is a block here and another block here, let's say this is block 1 and this is block 2. So if there is a transaction here, this block will have an ID. Let's say this block has an ID of 1 and this block has an ID of 2. So if there is a transaction in this block, it will be something like this. Student ID concatenated with 1. Okay, this is the idea of the first hash function here. Okay, and it will stay the same. It will be something and 1 student ID and 1 student ID and 1, and so on. So the idea proposed by the second student is that, let's say we are in the second block here, we, instead of concatenating the block ID of the current block ID only, we do the following. We concatenate the student ID with the ID of the previous block, the one here. So it will be 1 here, and the ID of the current block, which is 2. So it will always be student ID block 1 and block 1, which is the block before it, and block 2. So in case there is a third block here with an ID 3, a transaction here would look like student ID block 2, which is the previous block, and block 3, which is the current block. So what would be a benefit of such hash function? Basically, this ensures that this ensures that each hash knows its exact location. Not only that, this will kind of this will actually prevent double spending attacks. So a double spending attack is an attack where a user uses a transaction or spends a transaction more than one time. So how can this prevent such attack? Basically, it will keep track of each transaction and its location in the blockchain. So whenever a user tries to reuse a certain hash, the hash itself, the hash value will determine the location of this hash in the blockchain, and if it exists there, this means that it was already spent. Okay, let's go to part D in question 1. How would Bitcoin be affected if someone discovered a way to forge an ECDSA signature? An ECDSA is an elliptic curve DSA signature, digital key signature. So this is just like the DSA that was previously discussed in the course. Okay. So use ECDSA signature on an arbitrary message just given an ECDSA public key. So here the question says that what would happen to Bitcoin if someone discovered a way to forge the signature of its users. And it says assume it takes 30 minutes of computation to forge a signature. So what do we mean here by saying forging a signature? What does forging signature mean? Basically, it means that given a public key of a person P, for example, this forger can create a private key for this public key. Can forge a private key for this public key. So the question says here it takes 30 minutes. How is this important? Okay, so let's say basically that let's think of two cases. Case 1, this user or this person P is always pushing transactions, pushing hashes into the Bitcoin database or Bitcoin chain. And person P changes his private key every 15 minutes. Okay, so this person will keep using the same private key while sending hashes or whatever to the Bitcoin blockchain with the same private key for 15 minutes, and then he changes his private key. So if there is an Eve here that intercepts his public key or gets his public key and tries to forge a private key for him, and this process takes 30 minutes. So after 30 minutes, if Eve tries to create a transaction or do a transaction impersonating person P, the Bitcoin will discover the forge and will reject the transaction, since by then, after the 30 minutes, this private key would have been changed by the person P. So the forging process will fail, basically. Okay, let's go to a second case where, let's say, person P changes his private key every 1 hour, let's say. So the person P will use his private key with the Bitcoin blockchain in doing transactions every 1 hour. So in this case, when Eve intercepts the private key, this person's private key, it will take Eve 30 minutes. And in fact, Eve will be able to forge transactions impersonating person P for another 30 minutes till he changes his private key. So in this case, actually, it can be problematic for person P, or basically everyone else doing such thing in the Bitcoin blockchain. Okay. Now, let's read the second question. So the question says, Bitcoin mining pools invite a large number of miners to participate in the process of finding a block. So Bitcoin contains mining pools. A pool is a group of people mining together, trying to find or to break find hashes or to break a certain function. And in mining pools, each miner calculates hashes at their own hash rate. So hash rate is the computational power of each person. So each user in the mining pool has his own hash rate and submits these hashes to a pool manager. So the hashes are the output of the mining process, and those are submitted to the pool manager. Any submitted hashes that do not contribute to finding a block, the hashes that does not satisfy the target of the puzzle, are called partial proofs. A hash that leads to finding a block is called a full proof. In any case, once a block is found, the reward is divided among the miners according to the submitted partial proofs, which is proportional to each miner's hash rate. So the hash rate of each miner contributes to the amount of the prize he's going to take. So the more hash rate, the more part of the reward you are going to take. It is to be noted that the Bitcoin network specifies the puzzle difficulty according to the total number of miners in the network. Thus, if the number of miners increases, then the difficulty also increases, and vice versa. So basically, the mining process gets harder when more people are mining in this pool. Okay, consider the case of a miner who is a member of a particular mining pool. This miner submits only partial proofs and withholds full proof if it finds them. Does this miner provide more or less if it mines honestly, submits partial and full proofs? Okay, so what do you think will happen? So basically, if the miner does not submit all the partial and full proofs, basically the total outcome of this pool will be less, meaning that the total amount of reward being split among the miners in this pool will be less. So this miner will actually gain less because the pool gains less. Okay, what are the consequences to the mining pool itself? As we just said, since this miner is not submitting all the proofs, so the total output or the total number of solved hashes of this pool will be less, so everyone else gets less reward also. Okay, so what are the consequences to the overall Bitcoin network in terms of adjusting difficulty? So as we said before, the difficulty is related to the number of miners in the network, and also to the hash power, the hash rate or computing power of used in this network. So since he is not using his full hash rate, this means that the effective hash rate of the Bitcoin network will also get reduced, because now there is a portion of his total mining power not going to finding blocks, technically, since he's not submitting them. Thus, the Bitcoin network will eventually reduce its difficulty. Okay. Now, in part B in question 2, consider two pools, P1 and P2, with mining powers alpha 1 and alpha 2. So we have two pools, P1 here with alpha 1 computing power, and P2 with alpha 2 computing power, respectively. P1 decides to attack P2. So P1 decided to attack P2 by dedicating a portion of its hash power, called beta, towards mining for P2. So P1 decides to take part of the mining process in P2 without submitting full proofs for P2, only partial proofs. Thus, P1 gets reduced reward from its own mining, since it's not using its full hash power in mining for itself, but gets partial reward by mining for P2. What are the consequences for P2? So let's think of the effect on P2 now. Okay. So, since P2 with the number of miners inside it, so basically P2 had a certain number of miners inside it, where the reward was divided among them. Now that P1 has entered and started mining in P2, basically the number of miners in P2 increased, so the reward will get distributed among miners in P2 and P1. So P1 will take a share of the reward from P2. So the main consequence here for P2 is that P2 miners will get less reward. Okay, what are the consequences for the overall Bitcoin network in terms of adjusting difficulty? So now that, let's think of that in P1's side. So in P1's side, in pool 1's side, since more there is less hash power being used in the mining process, so basically the effective hash power is reduced in P1, meaning that the Bitcoin network will reduce the difficulty in P1, and that may benefit P1 since it will get more money with or more hashes with less computing power. And as for P2, depending on how much hash rate is being contributed to P2, the puzzle may get more difficult or may not. Okay, so can this attack be profitable for P1? The answer is mainly yes, but it may not be the case. So it all depends on the following. If the puzzle in P1, the difficulty of the puzzle in P1 gets reduced, so with less mining power, P1 gets better reward. than it should have with the old difficulty. If that happened and P1 gets a share of P2, so if this total, the total of P1 plus the share of P2 is big enough that it is bigger than the P1, let's say here this is the new P1. So if the new P1 after the reduced hash rate power being used in P1, the pool P1 plus the share from P2 is more than the reward output of using the full hash rate in P1. So in this case, yes, P1 can be more profitable in case of this attack. If this is not the case, then no, then P1 mining for itself will be better. Okay, let's read the answer here. So for P2, its total hash power remains unchanged by this attack. However, the reward now gets divided over a larger number of miners, which include the attackers. The effective hash power of Bitcoin is also reduced, leading to a lower difficulty. This can be profitable for P1 if the reward it obtains from P2 plus the benefit it gets from reduced mining difficulty outweighs the losses incurred from infiltrating P2. Okay, now with part C in question 2. Now, consider that P2 retaliates by taking the same action again against P1, dedicating a portion of its hash power to attacking P1. Assume that each pool has adjusted its infiltration rate to an optimum value where neither pool can increase its revenue by adjusting its own rate. So here it says that so here we have pool P1 and pool P2. Now after P1 started attacking P2, here started taking part of the process in P2, P2 decides to do the same and take part of P1. Okay, so now P1 is attacking P2 and P2 is attacking P1. And here the question says, assume that each pool has adjusted its inflation rate to an optimum value where neither pool can increase its revenue by adjusting its own rate. So, is P1 profiting more or less than scenario in part B? So in this case, where P2 is attacking P1, so basically P1 is not getting the full share of its full reward. So in this case, no, since P2 is taking part of the reward from the pool P1. So the answer is no, P1 is not profiting more. Okay, is P2 profiting more or less than the scenario in part B? So in part B, P2 was the pool that is being attacked, and it was mining only for itself, and P1 was taking a share from its reward. So basically, since it is attacking P1 now, so it is taking a share of the reward from P1, so it is profiting more than the scenario in part B. Okay, let's read the answer. P2 will profit more than the scenario in part B because now it will get some rewards from P1. Other than, on the other hand, P1 will profit less than the scenario in part B because some of its reward now go to P2. At the equilibrium point, both pools lose the same amount. So what does this mean? Basically, at the equilibrium point, there will be no point of each pool attacking the other one, and it may not be profitable doing so. So each pool will go back and focus on mining for itself. Okay, now with part D, question 2. Now both pools now have a choice between the following 4 strategies. 1. Attack if the other pool attacks. 2. Attack if the other pool does not attack. 3. Do not attack if the other pool does not attack. 4. Do not attack if the other pool attacks. Out of these 4 strategies, which one is the most profitable one, and which is the least profitable one? So let's go and check each one of these 4 strategies. Now, attack if the other pool attacks. So in this case, so if we have P1 and P2, if P1 goes and attacks, P2 will go here and also attack. So in this case, as we said, they will eventually reach an equilibrium state where neither one of them profits from the other one more than the other. So here there is no point of doing such attack at the end. So the second one here, attack if the other pool does not attack. So here, if we have P1 and P2, so if P1 attacks P2, let's say that P2 will not attack. So in this case, P1 will profit more than P2, and this will be a profitable case for P1 basically. This is number 1, and this is strategy number 2. So strategy number 3. Do not attack if the other pool does not attack. So in this case, P1 will not attack if P2 does not attack, and vice versa. So everyone will mine in its own pool. And this will technically have an equilibrium state just like the first one. The last strategy, do not attack if the other pool attacks. So this one says that if let's say P1 attacks P2, P2 will not attack. So is this a good strategy? What do you think? In this case, P2 will lose. So this is not a profitable strategy for P2, but it is in fact for P1. So which one is the most profitable and which is the least profitable? Let's try to think of it from the point of view of one pool of them. So if we are to think from the point of view of pool 2 in all the 4 strategies, in the first one, it's an equilibrium state for both of them, so no one is more profitable than the other, so no. So if in the second one, if P2 attacks P1, attack if the other does not attack. If P2 attacks P1 and P1 does not attack, so this one is profitable for P2. And in the third one, it's an equilibrium state, so no one profits more than the other. In the fourth one, if do not attack if the other pool attacks. If P1 attacks P2 and P2 does not attack back, so it will lose. So basically, this is the worst case scenario here for P2. So which one is the most profitable? It's strategy number 2. And which one is the least profitable? It's strategy number 4. Okay. Now with part E, question 2, and the last part for this tutorial. Now, the question says the idea of block withholding can allow miners to optimize their mining power. Consider the case of a miner that is dividing its mining power evenly over m mining pools. How can block withholding help this miner optimize its power? This form of attack is called lie and wait. So, how does this work basically? So let's say we have a miner M here, uh, and a miner, let's say miner M, okay, and this miner is mining in several pools here, P1, P2, P3, and it's distributing its hash rate among these three pools. So remember, the reward gets distributed among the miners based on the hash rate, the effective hash rate being used in this pool for each miner. So let's say while mining, the miner M found a hash. Let's say found a foolproof in P1 here. We found the foolproof. So if the miner M submit the foolproof with his current hash rate that is being distributed among the three pools, he will get his fair share of his hash rate divided by 3, for example, if they're evenly distributed. So instead of doing this, the miner uses the concept of block withholding, and whenever he finds foolproof here, he stops mining in pool 2 and pool 3 and uses his full hash rate, hash power, in compute in mining in P1. And then after a while, the miner M submits his foolproof, the one or the block he found. So in this case, he gets the reward of not the hash rate divided by 3, but his full hash rate. And then he does the same whenever he finds a foolproof or a block in any of the pools he is mining in. So that's it. See you next tutorial. Thank you.